So now we're moving into the user presentations where users have actually solved their own challenges themselves. And we have 3 presentations. The first of all was from Holger Busch, who I've known for a very long time, since my early formal verification days at Infineon and Siemens. And Holger Busch is going to talk about compatible qualification metrics with formal property checking. So I hand over to Holger now.
Thank you very much. Can you hear me? It seems so. I can hear myself at least. Yeah, so I'm going to talk about qualification metrics for formal property checking, because we introduced this also in the context of the ISO 262 requirements, where we have to fulfill these things, and that's an overview of my talk. So the question is, when we gave trainings in formal property checking, and people were asking for coverage metrics they were used to from simulation, at that time we didn't have a real answer for this. We simply said, well, everyone knows that formal property checking is exhaustive. There's no need for coverage metrics. But meanwhile, it's better known that it's, of course, you can be incomplete in formal property checking as well, only at a different level. So you can say in a certain respect it's correct. If you check a single formal property, then all combinations are really internally are checked by mathematical methods. But you can also say no, it's not 100% coverage if you consider the complete design under test, because your property assumptions typically are constrained, so they have assumption parts where you constrain some input scenarios, which if you compare this to constrained randomized simulation, you also define some constraints, and then it's stronger than this because you don't select just specific scenarios satisfying this constraint rather than satisfying the complete space within this constraint. But it's still only for this constraint, and we have other properties with other constraints, and you have to make sure that you have really covered all scenarios. And then the second place where it can become incomplete is that the commitments of your formal properties, which specify then the outputs, the expected output behavior, is also not necessarily complete. Because you might have some window in the execution of the property where the output is not seamlessly defined. So a single property itself cannot really cover all input-output behavior, and even if you have a set of properties, you cannot be sure if you don't apply other methods as well. So typically you develop the properties according to the functional clusters. You partition the design into clusters and cover the different partitions by different property sets. And then you must guarantee that the partitions you identify and the properties which describe them are really complete. It's a different level of completeness you have to provide, but you have to. So the different goals, you want to assess not just the completeness of the property set, but also for formal verification management, you must know, you want to track the progress, like simulative verification, whether in the middle of the time you plan for the verification, whether really the progress has been satisfactory or whether really there are certain problems you want to see that. And finally, you want to have some sign-off criteria, of course, when you can finish the verification. And we have mixed verification landscapes with different approaches like simulation-directed and constraint-driven randomized simulation and formal property checking. Even on single modules, we apply these mixed verifications. And of course, as Martin already mentioned, we have to satisfy the ISO 26262, which requires that we document all the verification. Therefore, we must find a way to keep all verification efforts traceable and from the requirements down to the properties, and show that all the requirements have been really verified. We must document all this. What are the classical approaches for formal verification? The most simple one is manual inspection of properties. But there's a problem, of course, because the other part who has to do the inspection must understand the properties, which is, if the properties are sufficiently simple, it's not really a too difficult task, but of course it's not really acceptable in terms of ISO 26262. Then the formal property checker we are using in Infineon is Onespin. There's a very special feature, formal completeness checks, where the completeness is really proven formally. This is very powerful, and then probably the strongest criterion is available on the market, but it's not at all related to the simulation coverage metrics. So if you do mixed verification, then it's difficult to combine the results with the results from simulation. And you can generate by formal property checkers, they are able to generate witnesses which are just like simulation traces, and you can run them in the simulator and then apply the normal coverage matrix. But this is also not really, it depends on the quality of the witnesses you generate. And then a different approach is to mutate the design, so inject some faults and check whether these faults are detected by the properties, or whether the properties just behave as before, they are simply proven, and then probably don't have done enough. And there are two approaches for this we are using in Infineon, which are based on this design mutation. First is a feature Quantify, called Quantify, offered by Onespin Solutions, a built-in feature to compute coverage. And the second one is Certitude, using Certitude, which is sold by Synopsys, which some of you may have heard of already. And I have some slides on both approaches following. So first, a little presentation of probably every one of you has seen some of the features of formal property checkers. I don't think that they are much different between different vendors. So normally, some property checkers support different property languages. There are standard languages like SVA and PSL around. And Onespin also supports these and has an own language, ITL, which has been developed just for formal verification. Is very easy to use. For us, if we use this for formal property checking, it's still easier to apply and better supported than SVA. So you can talk to a designer, and if he should do some basic verification, then ITL is a very simple language for him to use. And of course, linting is an attractive feature which shouldn't be underestimated, because it checks basic things like whether sensitivity lists are okay, or whether some signals are contained which do not occur in the process, or whether some signals are never read or never written, or something like this. This is also some basic functionality, quite useful. Then we have, like every vendor, these are the automatic parts of the property checking. So dead code determination and stockade signals and anything else you can think of and see. I think for most vendors, formal property checkers, see a similar functionality there. But of course, we do not use it just for this automatic formal verification, but really for full functional verification. So we have some IPs where really only formal verification is applied to verify all the functions. So I would just emphasize the automatic part of property checking there. Therefore, we have quite a powerful property debugger also, which has a lot of different ways of analyzing why properties fail. You get waveforms, you get annotated properties, and root cause analysis. So there's quite some functionality available which really helps to debug the failure of properties. And there's more recently, for coverage, we have the formal completeness checker. I talked about this earlier, which only Onespin has, as far as I know. And then there's a more recent feature, which is Quantify, which provides line and branch coverage, which actually is much more close to what what people want to see who are not so deeply in the details of the formal technology, but just want to get some data which looks similar to the simulation coverage data. So the Quantify feature from Onespin first does some pre-analyzes. So there's some identification of dead code, which is very helpful there because this has to be covered, and also constrained code. So code which, if all the properties have some global environment constraints of the module under test, then some of the code which has been implemented will never be used. So this code cannot be covered either. This really makes sense to have this view of constrained dead code. And redundant code reasons, some designs have redundant code which do not affect the results of some HDL process, and therefore also needn't be covered. And we get a very basic feature is to do some code reachability analysis by a given property set. And the kind of internal simulation is being done. And then the more stronger part of this, where really formal proving has to be done, is to compute observation coverage. So it checks not only that the code location is reached, but also that what is done in some HDL assignment really produces the result, and the result itself is also checked, whether this is checked by the property. So this is more refers to the output specified in the commitments of properties. So, and then you get a result internally. I don't want to, that's Sven's task to explain this in more detail, but from a user point of view, you get, you see that there are some proofs are being done internal, really formal property checking proofs are being done, and you see some of them failing and some of them hold, and the failing ones are those which add some result to the coverage, like you would expect if you are talking about fault injection. It's clear that something must fail, which normally doesn't fail. Yeah, the user guidance is very easy. It's just a push button feature. You can instrument it in a little, according to the code regions you want to focus on, or you want to skip, or you want to exclude. You can do this, but then you push the button and simply fire and forget and wait for the results, which can take a while, of course, like you would expect. And the result is then presented in different formats. You get XML format, which you can load down into UCDB database and merge with simulation metrics, and you get an HTML visualization, which you can then call in any internet browser. Like here, this is how it looks for a very, very simple example. You get some statistics on top for each module which is covered. You get some statistics of how the red lines are, the red ones is the code which has been detected to be not covered. Then you have different qualities, like some pieces of code might have just been covered touched by the simulation of the witness, but not by the rest. And, other parts, the really deep green ones are the ones which we want to see. But this code, finally, everything should be deep green. It's a very simple flip-flop example. I just added a very simple property, which just performs the write. That's probably you cannot see it, but it's just a VHDL with a process with a reset, and if there's a write signal, then the write is activated. The signal is written. The flip-flop is written with the write data. And with this one property, you already get most of this covered. But if you don't have the reset property, then you have non-covered code, of course. And this also this simple example demonstrates that it's not sufficient to. By the way, this demonstrates the difference to code coverage, because if you don't check which value has been taken, if you have a property, if the write is active, and then you prove true, this would activate this code, but it doesn't activate. It doesn't check the assignment when did this line. But if you then say yes, it has the previous data written to it, then you have to cover also the assignment. But this itself is also, even if everything is green here, this is not sufficient because you have not covered You could cover this fully, or if you just add a reset property, but don't have a property for the non-write case, so that the flip-flop just keeps its value if there's no write command, then this is all the code is covered, but it's still not complete. Yeah, and then we have a second approach using Certitude. Certitude has been developed by a French company, Certitude, originally, and was bought recently by Synopsys, or a year ago, I think. And yeah, they promised to develop it further, and we are using it and have introduced it in our flow also for simulation. Checking the quality of the simulation test benches, and this can also be used for property checking in a very similar way. So the instrumentation is exactly the same. It is based on fault instrumentation of the HDL. So for VHDL, you see here the original VHDL. You probably cannot read it, but it injects some arrow vector, and which each element of this vector, a different fault, is activated in the VHDL code here in this example. So some branching conditions are simply put to true if one component of this vector is 1. It's normally considered to be 1 hot, and then other elements of this fault vector will activate other faults. They're quite simple approach, but it's not so trivial to implement all the HDL design. And then the task is only to check whether all these activated faults are then found by the test cases. That's the way it's normally used. We have a lot of different phases first, because to make, you can well imagine, it can be quite inefficient if you have 10,000 faults inserted in the design. Each of them can be activated, and there should be, for each, should be at least one test case which detects it. But if you're unlucky, then you really have to run a lot of test case fault pairs until you really have covered all have detected all faults. So it's there's some optimization in this, some heuristics implemented in Certitude, where some activation phase is run. So modeling phase is the instrumentation of the RTL code activation phase. There the test cases just run once, and some coverage information is then extracted, which gives them a hint to Certitude to which test cases to select in order to detect which fault. So some very powerful heuristics are contained in there already. And then we have the actual detection phase, where in each single simulation, some test case fault pair has to be checked whether the test case really detects it. And then we have a quite interesting feature also, the matrix computation, where just for some samples with a range of plus minus 2 or 3%, you get with just a very limited set of faults which are run, you get a quite reliable statistics already, how much you can expect than if you run the full qualification. And if you apply this to formal properties, it's quite straightforward, because instead of the simulator, you just invoke the property checker, and instead of the test case, you offer it a property which should detect the fault. It's here written on this, so there's an interaction between the Certitude simulator or the formal property checker, which the formal property checker, of course, has to load the instrumented RTL and elaborate it, and then you get results, and Certitude manages all the results. And of course, you have to provide some scripting, how to combine. So Certitude doesn't know what is needed to invoke the simulator or the property checker. So you have to provide scripts which loads the right RTL, which do the instrumentation, or which activate the faults which Certitude selected. So it's a bit technical here. Normally, for property checking, you normally have a regular property, which is an assumption part and a commitment part. And then you run an augment property, which is an additional, in order to be able to run it on the instrumented VHDL design, where you just say the fault which has been selected by Certitude should be 1. All the others, it's 1 hot. All the other faults are not activated. And then you try to prove the same property as before. And if this property check now fails, then you know the property has detected this fault, and this is then interpreted as being detected by Certitude. And so it's no longer necessary to run the same, to activate the same fault with a different property, because Certitude already considers this fault C here to have been detected. And you can just consider the normal regular proof. You can do it on the instrumented design as well if you have the constraint that there's no fault activated. The fault vector is just 0. Yeah, that's it. Sounds quite easy, but it's not that easy to really do the scripting that this runs smoothly. Yeah, and then it terminates when all faults either have been detected or if all the fault property pairs have been exercised for non-detected faults, because obviously normally the property set is not fully complete, only if you have run the completeness checker before, but if you manage to do the completeness proof, then you can expect everything to be detected, but if not, then it's not possible. So here's a final comparison between both approaches. Quantify is a built-in approach. The added value is clear. You get really coverage results which are useful for productive verification. You get some holes where you see the properties have not covered code, and this is real value, especially if we have this multi-site verification partitioning. That's you have to some of the paths have been by different verification engineers or even by consultants. And you want to control the quality, and it's really necessary that you see if there are any holes in their verification, even at this basic level. And the design sizes are quite reasonable. We have large modules with 50,000 lines of code, which can be handled by both approaches. So it's quite powerful. Meanwhile, initially it was not that powerful, but meanwhile it is. The usage is for Quantify, it's very easy, but just push button. For Certitude, it's a little less easy. You need to set up as a complete environment, then you can do the rest in the same way as before. But for the first time, it's not easy. Fault injection is in Onespin. It's on the elaborated model or during module elaboration, or compilation of the model. The faults are injected, whereas in Certitude, as you have seen, it's explicitly done at RTL level, so you can see but you normally don't want to see because the VHDL becomes much longer than before due to the additional branches. User control is more rich, of course. In Certitude, you have a lot of parameters you can configure. It's the question whether you want to always to configure all these parameters. Probably per company you have to provide a normal set of parameters you want to configure. And yeah, maturity, of course, Certitude is quite mature because it has been in use for many years meanwhile. And our scripting is something we wrote on our own. So it's, of course, for internal usage. And I expect that there will happen more between Synopsys and other EDA vendors of simulators and also property checkers to add more to this combination. Yeah. So, and let's draw me the conclusions. I have time for this. So we have now two simulation compatible qualification methods for formal property checking, FPC, which is really ready for productive use, or we have been applying it for 2 years meanwhile. And both handle big IPs and property sets. So it's really usable. Therefore, we recommend strongly to use it. Either the one or the other method, but even both together we use, because the first one is very simple to quantify, and to do the other one to make it compatible to the simulation results. So these are two different paradigms, which maybe the EDA vendors have to consider for the future, which to follow. So Quantify is a built-in feature. Yet you can do much more in the property checking environment because this has the knowledge about the fan-in between properties as well, and the HDL design and the faults. Whereas if you do it in a separate way, like Certitude, Certitude doesn't have the knowledge about the properties. It just says can learn from the faults which have been detected by different test cases and then improve because the likelihood is bigger if some labeled fault is attacked by the same test case of property, but it's the same, then the likelihood is, of course, bigger than taking an arbitrary other test case to detect this property. Yeah, that's, I think. Yeah, so there are many potential synergies, many potential when combining both, but we have to discuss it in the future.
Thank you. Thank you very much, Holger.
Thanks.
Are there any questions? There's one at the back. I have a question as well, Holger, which I'll ask as I walk to the back. I've been working in formal verification for a number of years with you as well. I've always seen the problem in that dynamic verification is done here and formal verification is done here. It's very hard to combine the results. You see this as a good way of combining results?
Yes, I think so, yes. Because we actually have modules where it was not sufficient to rest just on simulation. Some scenarios were quite difficult to touch, to cover by simulation, and when an extra effort was spent by a formal verification engineer to fill in this coverage.
I am Tony from Infineon. I'm a verification engineer myself. I've used Certitude in one of the projects, and I feel, I just want to get your impression of the tool. And what it does is really what...
Quantify or Certitude? Or both?
Certitude. Quantify I haven't used, I don't understand how it does. But I feel that the kind of faults that Certitude introduces is mostly the kind of design errors that if I were to be a designer, I could commit such kind of mistakes while writing my code. As a verification engineer, I really don't understand what the fault means for the functionality in itself. And especially the problem is even more aggravated if you have more non-detected faults, let's say. So I would have imagined the Certitude would have introduced faults which are functionally, are sort of like a functional faults, rather than just flipping the bits or maybe tweaking the operators here and there, which is sort of like a design errors. Which the designer could commit and may not directly affect, I'm not sure, it's not relevant directly to the functionality in itself.
Yeah, but say it's a good way of guaranteeing basic verification quality, because if there are still coverage holes with this, and it's little more than, of course it's more than the classical code coverage, because it's really, the properties have to check the outputs, for instance, and this is already attached to functionality, but of course you don't check whether the specified functionality has been implemented in the same way the concept engineer wanted to have it. So you can cover the design by full 100% coverage, but of course there's no link to the specification as such. So this is a different question, how to guarantee this. But I think for getting the basic quality, where you perhaps have a bad feeling that the quality you get, maybe from consultants or somewhere, is not sufficient. And it's the first matrix which is applicable and which already has a value. But if you have a very experienced verification engineers where you do know they have been doing good work for years, then the value is probably less. But of course you cannot cover everything with this approach.
Okay.